How's it going, everybody? So I made this video already, but I can't find it. So in order to provide you with a full, complete version of this textbook, I'm going to re-record it. So this is chapter 3, section 3 of Algebra 2. And it's just continuing talking about graphs, just getting more comfortable with graphs. More specifically, this is just different properties of graphs. So we're talking about even graphs, odd graphs, we're talking about mins, max, increasing, decreasing, and then we're talking about average rate of change at the end. Kind of just randomly, in my opinion. But let's get into it. Here we have our first example. They just give us 3 graphs, and they want us to tell them if these graphs are going to be even, odd, or neither. So it gives us an opportunity to talk about what these types of graphs look like. So if it's going to be an even graph, that's the first one, it's going to have y-axis symmetry. So you can write that down. I'm not going to write that down. But if it's an even graph, it has y-axis symmetry. If you flip it over the y-axis, it lands back on itself. And you see that's what this graph does. It's just the same if you flip it over. So this one is even. That's an even graph. This one, however, is odd. So if it's odd, that means it has origin symmetry. Now, what does origin symmetry mean? That means if you flip it over both axes, it lands back on itself. So I like to look at one side. If you look at this side, you see if you flip it up over the x-axis, it would become something like that. And then if you flip it over the y-axis, it would land back on itself. So that's what an odd function looks like. You kind of get the feeling of odd functions, and you can kind of pick them out. So you know, like x cubed, that's an odd function. You know, like, maybe you don't know this graph yet, but the sine function, that's an odd function. As you see how if you flip it over the x and the y, it lands back on itself. But it doesn't have to be even or odd. It can be neither. So you see the one in the middle is neither. If it was shifted down to where the x-axis was right there, then it would be an odd function. It would be like a sine function in a way. But as it is, it's not. It's neither. It's definitely not even. It definitely doesn't have y-axis symmetry. And it's not odd either. It's an odd shape, but it's got to be in the middle for it to actually be odd. And so that's what the graphs look like for even, odd, neither functions. So here we're doing the same thing, but we just have the equation. So I'm pretty sure we've done this before. So let's remind ourselves that the way we tell if it's even or odd or neither from an equation is we plug in negative x. And if we just get out the same function as we started with, that means it's even. If we get out the negative version of what we started with, that means it's odd. And so, like, if we do if we find f of negative x, that's negative x squared minus 5. So negative squared becomes positive again. So we just end up with x squared minus 5, which is simply the original function. So that means that this is an even function. And let's see. Let's do c next. So we see with c, if we do f of negative x, we're going to have 5 times negative x cubed minus negative x. So we do our simplification here, but here it's a negative to an odd power, so that's going to stay negative. So we're going to have negative 5x cubed, and then negative negative becomes a positive x. And so we can definitely see that that's not the same as the original, right? But you also see that all of the signs are different. So if we would factor out a negative, then we would end up with the original function. So we ended up with negative f of x. And that is what happens when it's an odd function. You plug in negative x, you get out the negative y value. The opposite y value as you would when you plug in a positive x. And one thing to note here as well is the exponents. So if it's a polynomial, notice that both of these x values have an odd exponent, right? So it's got a cubed exponent, and then it doesn't show it, but that's got an exponent of 1. And so what's really happening is both of the signs are changing because you plug in the negative, and since they're both raised to an odd power, both of the signs are going to change. And you see that's different with the top one, and this doesn't show it either, but that's really x to the 0 power. Both of those powers are even. And so when we plug in the negative, the sign's not going to change, because when you raise it to a negative power, or when you raise it to an even power, it's always going to be positive. So the sign's not going to change, and it's just going to be an even function if the powers are even. And all of the signs are going to change, and it's going to be an odd function if all the powers are odd. Kind of like that's how they got their name. And then when you come over to one like b, here one of the powers is odd, the other power is even. And so that actually tells us right there, the powers aren't all even, and the powers aren't all odd. So it's neither. And if we plug it in, we should be able to see that. If we find, I guess that's g of negative x, we would have negative x cubed minus 1. So the negative would stay there. It'd be negative x cubed minus 1. So it's not the original function, because in the original function the x cubed is negative. And if we try to factor out a negative from both of them, we're not going to get the original function here either, because it's supposed to be a negative one, not a positive one. And so since both of the signs didn't change, we don't get the original function or the negative of the original function. It's neither. And then with d, I mean, for one, you should be able to picture the graph. But you know what happens with an absolute value graph. No matter what you plug into an absolute value, it's always going to come out positive. So it's always going to equal the same. It's not just going to equal x, it's just going to equal the positive version. So the absolute value, you take the absolute value of the negative is going to make the negative go away, because it always comes out positive. So we just end up with the original function. So this one is even. And if you picture the graph, you should know what the graph of that looks like. It's the v, which definitely has y-axis symmetry. So that was a quick refresher. Just that's how you're going to tell if it's even or odd with the equation. You're just going to plug in negative x. If nothing changes, it's even. If every sign changes, it's odd. So now we're just talking about decreasing and increasing. I mean, I think this is a really intuitive thing. It's not something to try to have to memorize. You just have to remember the graphs are always going left to right. Whenever you're looking at a graph, you're always thinking about it left to right. So when we're talking about increasing or decreasing, we're talking about going from left to right, from the negative x values to the positive x values. Because you can always think about x as time. So time goes forward. As time goes forward, that's always what we're looking at. So as we start from the far left and we go forward to the right, you see how the graph is going down. So, I mean, that's just English. That's decreasing. So we'll do our answers in interval notation. Pretty sure we talked about that from before. From negative 6 to 0, is that we will say that at negative 6 and at 0, it's not really decreasing. It's really kind of staying constant there. Maybe at negative 6 it's decreasing, but oh my god, it's not even at 0. It's going from negative 6 to negative 4. I don't even know what I'm talking about. From negative 6 to negative 4, it's definitely decreasing. At negative 4, it's flattened out, so it's not decreasing. So let's see, this will be our decreasing section. Our increasing, because then it starts increasing, right? And it actually increases all the way to 0. So this one is going to be that it's increasing from x equals negative 4 to x equals 0. And then the next thing doesn't happen in normal equations, but of course a graph with a piecewise function, you can make anything. Have we talked about piecewise functions? I don't know. But anyway, so constant. I mean, constant just means it's staying the same, right? And if you think about it, it can be either increasing or decreasing. If you look at this next section from 0 to 3, it's definitely not increasing or decreasing. It's just staying the same. And that's what constant means. You can look in the dictionary for that. So it's constant from 0 to 3. And then it starts decreasing again, right? It starts going down again after that. So we'll go back to our decreasing section and say also and union from 3 to 6. Actually, union is OR. But union, 3 and 6. So there we go. That's all we want, right? Increasing, decreasing. So just remember, you're always looking left to right on a graph. That's the biggest thing. And then again, really more English stuff. So local maximum. Yeah, so we got two different things. They're only asking about one of them here for whatever reason. But we've got two different things that we could talk about. We could talk about local versus absolute. Or some may say relative. I tend to say relative. So relative minimum, local minimum, versus the absolute minimum. So a relative minimum, I mean, what does minimum mean? Minimum means a low part, right? So when you talk about a relative minimum, you're not talking about the whole graph. You're talking about just like in one part, right? Like relative to the points around it, it's a minimum. And so when you look at that, that'd be like describing a point that looks like this. Relative to the points around it, it's the lowest. It goes down, and then once it gets to that point, it starts going back up again. And that's what a relative minimum is. So you'll see we have the same thing down here. It's going down, but then it starts going back up again. That's what a relative minimum is. So let's see, where do they ask about it? That's B, actually. At what values of x, if any, does f have a local minimum? List the local minimum values. So that's some important language too. So at what values of x does it have local minimums? Well, at x equals -1 and x equals 3. At x equals -1 and x equals 3. What are those minimum values? That's the y value, because the y value is the actual value of the function. So what are they? 1 when it's -1 and 0 when it's 3. So it is nice to list those as points a lot of the times, but this is fair just to emphasize how they asked it. But I say it's pretty good to say it's got a minimum at -1, 1, because that just says everything, and 3, 0. But then to bring this back to what we were talking about before, they're both relative minimums, but which one is the absolute minimum, the absolute lowest? So when you talk about the absolute minimum, that's just the absolute minimum of everything. I mean, it's in the word, right? And so just what's the lowest this graph goes? What's the lowest point? That's just right there. So this question doesn't ask for it. I'm sure the next one will. But what's the absolute minimum of this graph? Right there. It happens at x equals 3. And the minimum value of this function is y equals 0. The absolute minimum value of this function is y equals 0. And we talk about the maximums, it'll just be the same thing. So in this case, our relative maximum, where it goes from going up to start going down again, that's right there. So at x equals 1 is when it happens, and the value is 2. And then again, the question doesn't ask for it, but we'll go above and beyond the question, as we should always try to do. What's the absolute maximum of this graph? What's the absolute highest that this graph goes to? And well, there's not really an answer for that, right? Because the graph just keeps going up and up and up. So that'll happen. This graph just has no absolute maximum, because the graph just keeps getting higher and higher forever. So then lastly, just like we did in the last question, find the intervals where it's increasing and decreasing. Let's clean up the graph a little. So, not delete it. So let's do decreasing first. Where is it going down? So again, left to right. It is going down. Well, it starts for going down, right? Because don't be fooled by the arrow pointing up. The graph is going up, but remember, we're always looking left to right. So going left to right, if we were drawing the graph left to right, we'd be going down. We'd be decreasing to start off. So we're decreasing from -infinity, from x equals -infinity, all the way up to x equals -1. And then after that, we're going up again, right? We're going to start increasing. So we're going to be increasing from x equals -1 to x equals 1. But then we start decreasing again, right? We go back down. Because again, always left to right. That's the biggest thing about graphs. I feel like maybe that's what people have the trouble the most with graphs. You just remember you're always looking left to right. It's not like you're starting from the middle. Every graph on an XY plane you should think of it looking left to right. So that's how you know that now we're going up. Because we're looking left to right. If we continue drawing the graph, we'd have to draw up. So we're increasing from 3 forever, all the way to infinity. So yeah, the summary of this question, well, the increasing, decreasing part, same as last time. Always looking left to right. The minimum and maximum, I think that's just English. Minimum is lowest, maximum is highest. Relative means you're just looking relative to its area. So any small area. Like, it doesn't have to be a big area. It doesn't have to be just any area. You think about it as the hills and the valleys. This is the way that I think about it. If it looks like a valley, it's a minimum. Looks like a hill, it's a maximum. Alright, and that's what this is all about. So here we're not looking for the relatives, we're looking for the absolutes here. So this is an interesting thing that, I mean, you're just looking for the highest and the lowest point. So what I was going to say is interesting is, like, you have to include the endpoints, but of course you have to include the endpoints because you're looking for the highest and the lowest point. So, like, this first one, I mean, I'll just circle it. Honestly, if it's there, I'll just write it next to it. That's the max, right? That's the highest it goes. And this is the min. That's the lowest it goes. So a lot of these are interesting just because they point out the interesting stuff. So, of course, here, this is our max. That's the highest it goes. And then the lowest it goes, you see, this would be the lowest it goes, but there's a hole in the graph there. So there's no point there. And so, like, maybe you're tempted to then say, well, then the lowest it goes is just right before that point. But what is right before that point? Is it x equals 2? Well, x equals 2 is right here. You can't say it's x equals 2. Is it x equals 2.9? Well, no, right? Because you can always get closer. You can always get closer, so you can always get lower. So almost similar to how that other one was going up, this one's going to always be going down. Not to negative infinity, but it still always will be getting lower and lower. So this one has no minimum. Which is fine. You could say that it's always greater than 1, that the y value is always greater than 1, but there is no minimum. So here, similar to the other one, there's a maximum. But look at the minimum here. So some people may be tempted to say that this has no minimum. I would say that this has multiple minimums. This has an infinite minimums. This has the minimum in this whole range. It's got a minimum from x. So you write it like this, right? Anything between 1 and 2 will give you a minimum for this graph. This next one, it's got its absolute minimum right here. I wrote a W because it's a win. It's so obvious. And then there is no absolute max. And that's kind of obvious too. It just keeps going up and up and up. So there is none. There is no absolute max. This one, it ain't got neither. For it doesn't have any absolute max for the same reason we just did. It keeps going up and up and up. You might be tempted to say this point, but recognize that, like, no, because this point is higher. And you're always going to have points higher as that keeps going up. So this has no absolute max. And then the absolute min, it has no absolute minimum for the same reason we said for the other one. That it keeps getting lower and lower and lower, closer to that point, but it's still getting closer to that point and never actually hitting it. So the minimum value, like, it never gets all the way down to 2. It just gets closer and closer and closer to 2. So this has no absolute minimum either. It's got no absolute maximum or absolute minimum. Which is fine. Nothing wrong with that. All right, we got a couple more. So luckily, we get to break out the graphing calculator here. But that doesn't mean we get to stop thinking. It just means we get to look at the graph. So let's look at the graph. And honestly, they're going to look just like the ones we've already looked at. 6x cubed minus 12x plus 5. And what do they want? Approximate where it has a local max and min. So luckily, we're using a fantastic graphing calculator. So we can just tap it and it'll tell us, I guess it's still estimating, right? Because they're not necessarily precise decimals here. But what do they want? Where f has a local maximum and where it has a local minimum. Well, it's got a local maximum here, this negative 8.16. So at x equals negative 0.816, it has a local maximum. And at positive 0.816, it has a local minimum. And you can see the local maximum and local minimum values right there. So then where's it increasing or decreasing? Well, again, just remember, you're always looking left to right. So starts going up, so it's increasing from negative infinity up to right there, the negative 0.816. So it's increasing there. But then it decreases from that negative 0.816 to this point right here, positive 0.816. But then it starts increasing again, right? From 0.816, positive 0.816, it starts going up again, all the way to infinity. So there we go. So we still had to think about it. We still had to look at the graph like we have the other ones. But we got to look at the graph on a graphing calculator, which is always fun. All right, so now we got average rate of change. So, see, we don't really need the calculator for this one. So what is average rate of change? Well, that's a great question. So, average change. So think about what you're going to do. You're going to do how much is the value of the function changing over this x period. So let's see. For the first one, when x equals 1, what is f of 1? Well, 3 times 1 squared, that's 3. And then what is f of 3? That's 3 times 3 squared, that's 27. So what was the average change in that value? Well, how much did it change by? It changed by 24, right? And how much did the x change by? It changed by 2. So to be clear, we did 27 minus 3 over 3 minus 1. And that got us to be 12. And that's the average rate of change. So it's on average. So they're thinking when x changes by 1. Like I said earlier, x is always like the time. So you could think about this in like miles per hour. Average rate of change, average rate of speed. That's like a miles per hour. Change in the value over time. So we could write that even more to say it's the change in the y values, the difference in the y values, over the difference in time. Or in this case, time is x. And look at that. That's pretty familiar, right? That's the slope formula. Because average rate of change is just the slope. Slope is rate of change, right? It's just for a line normally. But here, we're talking about looking at this graph. So this graph looks something like this. They're talking about looking at this point here at x equals 1. Looking at this point, call it x equals 3. And they're talking about what is the slope of the line between those 2 points. That's what average rate of change is. It's the slope. And so, of course, I don't want you to just memorize formulas, but the kind of formulaic idea for this is f of 5, the one y value, minus f of 1, the other y value, when x is 1 and when x is 5, divided by 5 minus 1. That's the way I like to think about slope, because it just looks so clean and concise. You just know that's what it's going to be. But why is it going to be that? Because it's the change in value divided by the change in time difference. Change in time. But then you just have to calculate it from there. So you got to flex your mental math muscles. 3 times 5 squared, 75. Again, minus 3 over that change, which in this case is 4. So that's 72 over 4, which is 36 over 2, which is 18. And so that is our change in y over change in x, on average, between those 2 points. And now that we get the idea, we can just use that kind of formula for this one. So f of 7 minus f of 1 over 7 minus 1. So f of 7, 3 times 49, 147, because it's 3 times 50 minus 3. And then now minus 3 again, over 6 this time. So what is that now? We have 144 over 6. So that's 12 times 12 divided by 6. So that's 2 times 12. So that's 24. Again, change in y over change in x. So this is really important when you get to calculus too. You're doing this all the time. You call it a secant line. I mean, you could call it that too here. It's a secant line, just connecting 2 points. And when you find the slope of that, that's the average rate of change. Or if you had a function representing the position, you do that. That's the average velocity of the thing you're talking about. And I thought we were about to do that here, but no, we're about to go to Desmos to do some cool stuff. So suppose that g of x is that. Find the average rate of change of g from -2 to 1. Okay, we can do that. You see, we'll do just like we did last time, now that we have it down as a formula. And remember with slope, too, the nice thing is it doesn't matter which one you do first, as long as you match them up properly. So we can just will be just fine to do g of -2 minus g of 1 over -2 minus 1. And we just got to do that out. So that's -3 on the bottom. Let's see, more mental math flexing. So you plug in -2, you get 12 plus 4 is 16, plus 3 is 19. And then you plug in 1. 3 minus 2 is 1, plus 3 is 4, minus 4. So it worked out nicely. 15 over -3 is -5. That's our average rate of change. Ooh. So now find the equation of the secant line between those 2 points. And nice, see how they even represent the y value as g of -2. So yeah, let's do that. What's it going to be? Well, we're going to have... How do you write the equation of a line? You need a slope and you need a point. We just found the slope, so -5. And then we'll use point slope form. I think we've talked about it enough, right? We remember what it is. So it's x minus the x value, and we can use either one, equals y minus the y value, which was g of 1, as we use the x equals 1, so 4. And that's the equation of the line right there. They didn't ask for it in any specific form. But there we go. So now, let's go to Desmos, because part C, bring out the graphing calculator. They want us to, what, draw the graph of g? Yeah, I was going to do all that anyway. So g of x equals 3x squared minus 2x plus 1. And so here's the whole idea. We wanted from... Let's see. This is great with Desmos too here. Let's just full screen it. So what are we going to do? We want to do the 2 points first. So where were we at? We were at the point -2, comma, watch this, g of -2. Boom. So it can interpret that since we defined the g function. Let's do the other point. The other point was 1, x equals 1. So 1 comma g of 1. There's the other point that they were talking about. And what was the equation of our line? -5x minus 1 equals y minus 4. Hang on. Alright, so this is one of the fun parts now in math, where we get to find where we messed up. So, why does not go through the point 1 comma 4? Did I type in the equation wrong? I think that's what happened, isn't it? 3x squared minus 2x plus 3. 3x squared minus 2x plus 3. There we go. I typed in the equation wrong. So you see we don't have to adjust the points because we did it based on what g was defined as. So there we go. We said we wanted to find the average rate of change between -2 and 1. Then we use that average rate of change to write the slope of that line. So that's pretty cool. That's really everything we need to talk about in this section. But while we're here, I want to give a little preview of the coming up video this weekend of how to make a nice little visualer for calculus on Desmos. So let's start out, and this is a good example here too. So what we're going to do is, instead of doing this between 2 specific numbers, it's actually going to be really easy. We're just going to make it so where you can move it around. So we're going to have a and g of a, and then we're going to have b and g of b. And then we're going to add sliders for those, and we can actually even drag around the points. So you see now we have these 2 points we can drag around. And then we just have to set this up better. So instead of using 1 and 4, we're going to use a. We could use b or a, because remember it doesn't matter which point, but we'll stick with a. So a and f of a. So you see now, g of a. Why did I do g? G of a So the question said G. So you see now what's happened is now we have this line that'll always go through that point with the A value. But now we have to calculate the slope. So instead of the slope always being -5, we'll do exactly what we did before. We'll have our slope is G of A. Should have done parentheses in the beginning. We'll do them at the end. G of A minus G of B. And now if we close parentheses, it'll do it right. And then divided by A minus B. And there we go. Look at that. Now we've got the line between these 2 points. But the line is, the 2 points are always on the graph. So isn't that neat? That's just using the same concept we did. Just using the beauty of Desmos sliders. And you see, this is what I'll show you all how to do this weekend, where you can make it to where you move these all the way together, and it becomes the tangent line. Right now, if we move them all the way together, the line will actually disappear. See, we don't get the perfect tangent line, but ain't that close. This weekend, I'll show you how to do it all. That was section 3.3. If y'all are still around, you should do all these things up here. How do I point to it? Up there. And hopefully I'll get to see y'all tomorrow, where I will continue chapter 3 of Algebra 2.